Imagine a moment before time, a single, blazing point of infinite possibility. Then, 13.8 billion years ago, it erupted, the Big Bang. From this cosmic spark, everything began. Let's hear from an expert who spent years unraveling this cosmic dawn.
With the Big Bang itself, it was an equal competitor to the steady state theory for decades, until we finally got some evidence to support the Big Bang, and that was the famous cosmic microwave background. This is a leftover signature from an explosion that started in one hot primeval fireball.
13.8 billion years ago.
Thank you, sir.
Okay.
You don't need me for this.
No, that was the only thing I remember.
Sure, it was 13.85. You're showing off now.
No,
you're showing off. Okay. Right. So it was given as a funny pejorative name, but it stuck, and
right.
If it fits, it fits. Now, it's not clear how much noise it would have made, because just the expansion of space itself is not, that's not associated with noise. And space is vacuum anyway, and noise doesn't propagate. So if you don't want to call it the Big Bang, because it was probably made no noise, you
think you'd fix that by now.
No, you call it how about the main event?
Space, time, and the seeds of all we know. What journey unfolded from that fiery dawn? Join us as we trace the universe's evolution, from chaos to the stars we see today. A story vast enough to humble us all. The Big Bang wasn't a blast in space. It was space itself bursting into existence. Smaller than an atom, hotter than a trillion suns, this pinpoint stretched in a fraction of a second. Science tells the tale. The cosmic microwave background found in 1965 whispers of that searing birth. Galaxies racing apart, measured by Hubble in 1929, show it's still growing. In those first moments, particles flickered into being. Protons, neutrons, the building blocks of all matter. From a raging inferno, order emerged. Cooling over eons, the universe fused protons and neutrons into hydrogen and helium, the seeds of future stars. After 380,000 years, atoms took shape, freeing light we still detect as the cosmic background. Over millions of years, gravity wove gas clouds into the first stars and galaxies. The James Webb Telescope now peers into that dawn, revealing the universe's earliest chapters. Today, 13.8 billion years on, we live in a universe of marvels. 2 trillion galaxies, each a symphony of stars. It's stretching faster, pushed by dark energy, 68% of everything. Dr. David Spergel explains how this invisible force shapes our cosmic home.
It's the middle of the night, and you see lights on a distant shore. Now, those lights tell you that the shore exists, but it doesn't tell you anything about it. There could be mountains or jungles, you just don't know. This is the situation with dark matter. The luminous material in our universe, the stars and galaxies, tell us that dark matter exists, but it doesn't tell us what it's made of. Now, taken together, there's so much evidence for dark matter. I could spend the rest of this episode going over all the evidence. I mean, I wrote a book about it. And check this out. There's the rotation curves of galaxies. There's the temperatures of galaxy clusters. There's the bending of light around massive structures. There's the large-scale structure of the universe itself. There's the cosmic microwave background. It goes on and on and on and on. We know that dark matter exists, but we don't know what it is. But we do know what it isn't. It's not just normal matter that happens to be dim and hard to see, like rocks or planets or black holes. We know this because we've made measurements of the very early universe that tell us how much normal matter is in the universe, and there simply isn't enough to account for all the gravitational effects. Instead, dark matter has to be cold and collisionless. Cold means that the dark matter moves slowly compared to the speed of light. And collisionless means that it doesn't interact with itself or normal matter. That means dark matter is everywhere. Dark matter particles are streaming through this room right now. We are swimming in an ocean of dark matter particles. But because the dark matter doesn't interact with normal matter, we can't directly detect it. We can only learn about it through indirect methods.
In this vastness, Earth's fragile life bloomed, a fleeting miracle amid the cosmic expanse. With Hubble and James Webb, we look back billions of years, seeing light from the universe's youth. We're brief travelers in an ancient tale. From a single spark to a boundless sea of stars, the universe has evolved, a saga of creation and wonder. We're stardust, gazing at our origins through time's vast mirror. This is our story, a chapter in an unfolding epic. What mysteries lie ahead? As we marvel at the universe's vast evolution, another question tugs at our minds. Could we bend time itself? From the cosmic tapestry of stars to the fabric of space-time, what if we could travel through it, past, present, or beyond? Let's leap from the universe's birth to the enigma of time travel, science, fiction, or something stranger still. What if you could step into yesterday or leap to a distant tomorrow? Time travel, once pure fantasy, haunts our dreams and science alike. From Einstein's relativity to wormholes and cosmic loops, could we unravel time's arrow? Through tales like Back to the Future and Interstellar, we'll explore. Is this science, fiction, or a paradox waiting to ensnare us? Albert Einstein cracked time's code in 1905. It's not fixed. His theory of relativity showed time slows near massive objects or at high speeds. Astronauts on the ISS age slightly less than us, seconds, but real. In Interstellar, a minute near a black hole stretches to years on Earth. This isn't fiction, it's science, proven by clocks on speeding jets. Could we stretch time further to travel it? Beyond relativity, wilder ideas emerge. Wormholes, tunnels through space-time, could link distant eras, a shortcut to the past or future. In Avengers, Endgame, heroes jump timelines through quantum tricks. Spinning black holes might twist space-time into closed loops, letting us revisit yesterday. Scientists like Kip Thorne say it's mathematically possible, but building one, that's where reality blurs into the unknown. But here's the catch: paradoxes. The grandfather paradox asks, if you travel back and stop your grandfather's birth, how do you exist? Back to the Future wrestles with fading timelines, fun but messy. Some say parallel universes solve it. Each trip spawns a new reality. Others argue time resists change, a cosmic guardrail. From cosmic stars to the fabric of space-time, let's explore time travel with Michio Kaku.
In that case, time travel is something you have to take very seriously, because Einstein's equations do allow for time travel. And they're blueprints, blueprints for different kinds of time travel designs that are compatible with Einstein's theory. For example, gigantic spinning cylinders. You go around the cylinder and you come back before you left. Colliding cosmic strings. You wind around these cosmic strings and you come back before you left.
And the key element is that in Einstein's theory, it allows this under certain solutions?
That's right. Time and space are like a fabric, like rubber, like a trampoline net. However, if you stretch the trampoline net so much, it can rip, perhaps. And perhaps you can turn this trampoline net into a pretzel and allow yourself to go backwards in time. Now, of course, there's a catch. There's always a catch in these things. The energy, the gasoline necessary to do this is fabulous. Even an atomic bomb does not have enough energy to drive a time machine. For a time machine, you need the energy of an exploding star.
How about all the logical paradoxes that one would come across in time travel, going back to the past, killing your grandmother, and all of those kinds of issues?
Or meeting your teenage mother when she's a teenager and she falls in love with you. So how can you be born if your teenage mother just fell in love with you? There are two ways to resolve these paradoxes. The first is self-consistency, that if you want to shoot your parents before you're born, there's something preventing you from pulling that trigger. Maybe there's a hidden law of physics that says you cannot create a time paradox. I don't believe that.
Yeah, that seems far out.
That's far out. I believe that the river of time forks into two rivers. If you saw Back to the Future Part 2 very carefully, Doc Brown, this Einstein figure, goes to the blackboard and draws a timeline from the 50s to the 80s. And then he draws a separate line that splits off from the main timeline. The river of time forks into two rivers.
Is this getting to the so-called many-world interpretation of quantum mechanics? Would that be?
That is the simplest way to resolve all these paradoxes.
That never seemed very simple to me.
Well, it's the simplest in the sense that you don't have to add any other assumptions other than quantum mechanics. So if you go backwards in time and save Abraham Lincoln from being assassinated in the Ford's Theater, you've saved somebody else's Abraham Lincoln, who's genetically equivalent to your Abraham Lincoln, but you've entered another universe. If you shoot your parents before you're born, you've shot somebody else's parents before you're born, who's genetically equivalent to your parents. So you can go backwards in time continually, monkey with your own past. However, you're monkeying with, in some sense, a parallel past.
Right.
Now, Stephen
Maybe
Hawking...
creating a parallel.
Creating a whole new
universe.
That's right. And Stephen Hawking even said there's got to be a laws of physics preventing this thing from happening. Well, we've tried and tried and tried and failed. We cannot find any law of physics preventing you from going backwards in time. It seems to be consistent with the known laws of physics. The trick is you have to have this energy on the scale of a star. You'd have to be a very advanced civilization. So these tourists from the future are just not 100 years into the future. These tourists from the future would be perhaps millions of years in the future, the ability to control the output of a star. We physicists are hot rodders of physics. We push the equations until they break down. So Stephen Hawking assumed that they would break down. Well, we were shocked. They didn't break down. The laws of physics seem to be compatible with time machines. This is very unsettling because it means that perhaps, just perhaps, time travel is possible for advanced civilizations. It cannot be.
Science can't yet answer, but the riddle twists our minds. Time travel dances between science and dreams. Einstein bent it, wormholes tease it, and paradoxes guard it. From Interstellar's black holes to Endgame's leaps, we glimpse what might be. Is it real or a tale we tell ourselves? For now, it's a mystery on the edge of possibility. What do you think, fact or fiction? Share below and join us for more cosmic wonders.